What happens when you push matter to its absolute limit? Not just squeezing it, but crushing it so completely that atoms themselves can't exist. This isn't a thought experiment. It's the reality inside a neutron star. These are the leftover cores of massive stars, and they are less like objects and more like natural laboratories for extreme physics. We thought we understood the basics: unimaginable density, rapid rotation, but the more we look, the more these cosmic ghosts defy our models. They challenge our understanding of gravity, magnetism, and the very nature of matter. If you enjoy exploring these deep cosmic puzzles, a simple like and subscribe helps our community grow. Today, we're looking at why neutron stars are far weirder than we ever imagined. In 2022, astronomers utilizing the Murchison Wide Field Array identified a new and unusual radio signal arriving every 22 minutes. Repeating signals themselves are not strange. They are often the signature of pulsars. These are spinning neutron stars that sweep beams of light across the universe, much like a lighthouse beam. This particular signal, however, raised questions. When scientists examined archival data, they discovered it had been steadily arriving at Earth since at least 1988. This profound stability is not what physicists expect from a pulsar that rotates so slowly, taking 22 minutes to complete one turn. It indicated that whatever this object was, it was not a typical pulsar. The source of the signal, which has been named GPMJ 183910, is approximately 18,000 light-years away from us. The pulses of radio waves we receive from it are inconsistent in their length. Some last for only 30 seconds, while others can continue for a full 5 minutes. The arrival time also varies. The pulses tend to arrive within a window of just over 6.5 minutes, which is centered on that 22-minute mark after the previous pulse. While this might sound erratic, the dynamics of neutron stars are incredibly complex, and many different factors can influence the duration and arrival time of the signals we manage to detect. By analyzing data that spanned 35 years, astronomers were able to look past these short-term variations and average them out. This allowed them to calculate the object's precise rotation period, 21 minutes and 58 seconds. They also searched for evidence that the object was slowing down. It is expected that any spinning object radiating energy into space will gradually lose momentum and rotate slower over time. But the results were baffling. They found no detectable slowdown. Their calculations were so precise that they could only conclude that if the object had slowed, its rotation period had not increased by more than 0.28 milliseconds over that entire 35-year stretch. This is an almost unimaginably small change, proving the object is spinning with remarkable stability. This level of consistency, by itself, is not odd for a pulsar. Many are known as the universe's timekeepers, functioning as natural cosmic clocks because their timing is so reliable. However, that reputation belongs to pulsars that spin incredibly fast, sometimes hundreds of times every second. This stability is extremely odd for an object rotating as slowly as this one. To understand why this is such a significant puzzle, we first need to review the basics of how pulsars work and what forces cause them to slow down. Pulsars are a type of neutron star. A neutron star is the leftover core of a dead supergiant star. Setting aside black holes, they are the densest objects in the entire universe. To understand this, consider that the atoms making up our world are over 99.999% empty space. This is the vast separation between the tiny, dense nucleus and the electrons that orbit it. Now, imagine an entire star that is made only of the neutrons found in that nucleus. No electrons, no protons, and no empty space. The resulting material is so heavy that a single teaspoon of it would have as much mass as 11 times the entire human population, all 8 billion people. A standard neutron star might have 35% more mass than our own sun, but all that mass is compressed into a sphere with a diameter about the same length as the island of Manhattan. To call this dense is an understatement. For reasons that are still being studied, this extreme environment also generates an incredibly powerful magnetic field. This magnetic field is the engine that generates the signals we receive. The process that creates the light from a pulsar is complex. It involves an exponentially growing shower of light and matter, all spawning from a single electron. This process begins near one of the neutron star's magnetic poles. There, the magnetic field can accelerate an electron, forcing it to emit a particle of light known as a curvature photon. This emission effectively marks the start of a pulse. This photon then travels in a straight line. As it moves, the angle between its path and the magnetic field line it came from grows larger. When this angle reaches a specific threshold, the photon's energy dissipates and converts directly into matter. It creates an electron and its antimatter particle, the positron. This new electron-positron pair then immediately disposes of its own momentum by emitting 2 new photons, known as synchrotron photons. These 2 photons then travel, reach the same threshold angle, and each one creates another electron-positron pair. This process repeats, creating a cascade that grows exponentially, rapidly multiplying the number of photons and electron-positron pairs. The chain reaction only stops when the photons being created no longer have enough energy to produce new pairs. These resulting photons are what beam out into space. Meanwhile, the original electron continues its journey along the magnetic field lines, generating more curvature photons and starting new cascades. This pair production cascade is what makes the light of a pulsar so intense that we can detect a signal from this tiny stellar remnant, even from thousands of light years away. This process, however, explains the source of the light, but not why we observe it in pulses. We do not detect a continuous, steady glow. Instead, we see flashes. The reason for this pulsing behavior is that the magnetic poles of a neutron star are rarely, if ever, aligned with its actual axis of rotation, the imaginary line it spins around. Our own planet Earth operates the same way. The magnetic North Pole, which our compasses point to, is not in the exact same location as the geographic North Pole, which is the center point of our planet's spin. This misalignment on the neutron star means that as it rotates, its beams of light, which originate from the magnetic poles, sweep across the cosmos. They function exactly like a great cosmic lighthouse. For a distant observer, like our telescopes on Earth, we are not continuously in the path of that beam. We see the beam sweep past us as a flash of light, followed by darkness as the beam points away, and then we see the beam again as the star completes its rotation. These repeated, rhythmic flashes are the pulses that our radio telescopes can detect. The light that is produced by these energetic cascades is not the kind of light our eyes can see. It has very long wavelengths, which places it firmly in the radio part of the electromagnetic spectrum. This is why it can only be detected by specialized radio telescopes, not optical ones. This radio light also has special properties. It is coherent, which is a technical way of saying that the peaks and troughs of all the individual light waves are fluctuating perfectly in unison. Furthermore, this light is polarized. This means all the light waves are physically aligned or oriented along the very same axis. This specific combination, a coherent, polarized radio signal, is a known and trusted hallmark of a neutron star. And the 22-minute signal we are analyzing, GPMJ 183910, shows exactly this polarization. It also exhibits other unusual fluctuations. These are shorter bursts, lasting anywhere from 0.2 seconds up to 4 seconds. During these bursts, the axis of the light's polarization suddenly flips by exactly 90 degrees. It becomes perpendicular to its original orientation, and then, just as quickly, it flips right back. This strange behavior might seem random, but it is not. This polarization flip is yet another distinct signature that astronomers associate with the energy cascades happening at the poles of a pulsar. At this point, it would be easy to conclude the investigation. So much of the collected data points directly to a pulsar. We have the radio waves, the polarization, and even the signature 90-degree flip. This might seem like a solved case. However, there is one major variable, which we mentioned earlier, that throws this entire neat theory into doubt. That variable is the object's extremely slow rotation. To be precise, the problem isn't just that it's slow, it is the specific combination of that incredibly slow rotation rate and the high stability of that rotation. Here is the core of the problem. As pulsars shine their powerful beams out into the cosmos, they are radiating energy. They are losing it. The fundamental law of conservation of energy dictates that this loss of energy must have a consequence. The consequence is that the pulsar's rotation must slow down over time. This process continues for millions or billions of years. Eventually, the pulsar will be spinning so slowly that it no longer has enough remaining rotational energy to power those pair production cascades. The engine fails. At this critical point, the light emission process shuts off entirely. The beacon goes dark. When this happens, astronomers say the pulsar has entered the Death Valley. When scientists analyze the pulsar population, they often plot them on a graph to visualize this concept. They typically place the rotation period, how long one spin takes, on the horizontal x-axis. Then, they plot the rate of change of that period, how fast it is slowing down, on the vertical e-axis. The Death Valley appears as a distinct gray band that runs diagonally through this graph. According to all our established models of physics, any pulsar whose properties landed below this line should be inactive. It should be switched off. It simply should not be shining as a bright beacon. The signal we are detecting, GPMJ 183910, falls decisively below this line. In fact, it is well below even the lowest boundary that marks this Death Valley. According to our models, it should be well and truly switched off, and yet we are detecting it. To put this in perspective, let's look at the cluster of other known active neutron stars on this graph. The vast majority of them spin very fast, anywhere between 10 times every second to perhaps once every second. In sharp contrast, our signal has a spin rate of only once every 1,318 seconds. This is more than 1,000 times slower than a typical active pulsar. This slow speed, by itself, wouldn't be impossible if it was also slowing down very, very quickly. A rapid loss of energy, and therefore a rapid slowdown, would provide the raw power necessary to keep the pair production cascade running. On the graph, this rapid slowdown would move the object's data point upwards, placing it safely above the Death Valley. But that is not what we see. This object is not slowing down rapidly. As we established, it is mind-bogglingly stable. This makes no sense. We are detecting a signal that, according to our understanding of physics, should not have nearly enough energy to exist. The astronomers who discovered this signal were, of course, aware of this paradox. They considered an alternative mechanism. Perhaps this object is not a standard pulsar. Perhaps it is a magnetar. A magnetar is a very specific and rare type of neutron star. Its defining characteristic is an unusually, almost impossibly strong magnetic field. These fields can be greater than 10,000 times the strength of even the weakest magnetic fields found on other neutron stars. Magnetars are known to be violent and unstable. They famously undergo events called starquakes. These are cataclysmic releases of energy that happen when immense tension in the star's rigid upper crust is suddenly released. This stress builds up for two main reasons: the incredible pull of the magnetar's own magnetic fields and the slowing of its rotation. Just like any fast-spinning object, a young, fast-spinning star will naturally bulge at its equator due to centrifugal force, distorting it from a perfect sphere. As the magnetar ages and slows down, this bulge must shrink. The solid crust needs to readjust to a new, more spherical, stable shape. Eventually, the stress is too much, and the crust violently snaps into a new position. This event causes the magnetic fields to realign temporarily, and in the process, it powers the release of a truly massive amount of energy, which radiates away as light that we can detect on Earth. To give a sense of the scale, the most powerful starquake ever detected came from SGR 1806-20 back in 2004. That single event released so much energy that if it had taken place only 10 light years from Earth, it would have triggered a mass extinction event. If any phenomenon in the universe is powerful enough to light the beacon of an otherwise dead pulsar, it would be this. So, could GPMJ 183910 be a magnetar that has undergone a recent starquake? Have we resolved the mystery? It appears not. There are two major problems with this hypothesis. First, we expect these incredibly powerful starquakes to also emit huge amounts of high-energy light, specifically in the X-ray part of the spectrum. However, when we look at the source's position roughly 18,000 light-years away, no X-rays can be detected. The second problem is the timeline. It simply does not make sense for a magnetar outburst to continue for 3 decades. A starquake is a sudden, temporary phenomenon. The energy is massive, but it dissipates relatively quickly, within a few years at the absolute most. It is simply incomprehensible that this signal would have existed stably for at least 35 years if it was, in fact, a magnetar. The duration is wrong. Once again, the unique properties of our signal seem to exclude it from fitting our known categories. It does not behave like a standard neutron star, and it does not behave like an unusually powerful one that has undergone a special event, such as a starquake. If the signal is not being generated by a standard pulsar, and it is not the result of a violent magnetar starquake, then what else could possibly be its source? The astronomers who made this discovery have considered other, less common, alternatives. One possibility is a highly magnetic white dwarf. A white dwarf, like a neutron star, is a type of stellar remnant. It is what is left over after a star of a certain size dies. However, it is formed from a star that did not have enough mass to trigger the final, complete collapse. Its atoms are squeezed together incredibly tightly, but they do not break down. The empty space within the atoms is not eliminated, which is what happens in a neutron star. In theory, a white dwarf that possessed an exceptionally powerful magnetic field could generate radio emissions. And, critically, because it is not a neutron star, it is not bound by the same physical rules. It is not subject to the Death Valley concept. This means it could, conceivably, be as slow and as rotationally stable as the object we are detecting, all while still producing a signal. The primary issue with this hypothesis is the required strength of that magnetic field. It would need to be stronger than any magnetic field we have ever spotted on any white dwarf in the universe. Our observations just don't support it. There is only one known white dwarf that actually acts as a radio pulsar, and its radio emissions are approximately 1,000 times less luminous or less bright than the 22-minute signal we are currently analyzing. This is not a small discrepancy. It is a gap so enormous that it makes the white dwarf explanation seem highly improbable. What other options are left? Astronomers have, on rare occasions, observed very low-frequency radio waves coming from other types of cosmic interactions. For example, signals can be produced by the complex magnetic field interactions between a star and a closely orbiting exoplanet. Faint signals have also been detected from a binary system of two brown dwarfs, objects larger than planets but smaller than stars rotating around each other. But these emissions are on a completely different scale. They are typically around 100 million times weaker than the powerful source of our 22-minute signal. This is not a viable explanation. The energy is simply not comparable. In the end, it seems that none of our current, established theories can adequately explain this signal. An unresolved question like this, while it might feel frustrating, is precisely the kind of mystery that astrophysicists actively search for. It is a sign that something is wrong. When scientists discover new data that directly challenges our long-held theories and models, it signals that our understanding is incomplete. This is how scientific revolutions begin. In this specific case, our already somewhat shaky understanding of neutron star physics is being directly challenged. The astronomers who found GPMJ 183910 are confident about one thing: the relative ease with which they identified this signal, once they knew what to look for, implies it is not a complete anomaly. It suggests that similar sources are likely out there, hiding in the plane of our galaxy, just waiting to be identified. It is very possible that, just like this signal, many other similar signals are already lurking in the vast archives of data that our telescopes have collected over the past decades. Finding more of these objects, building a population of them to study, is the critical next step. This will be the only way to shed new light on the physical process that is powering this emission, a process that seems to operate far beyond the known limits of the neutron star Death Valley. Whatever lies behind this signal, it is almost certainly an entirely new phenomenon, something we have never had the chance to see before. How much would a person weigh on a neutron star? These objects, as we've discussed, contain the densest matter in the known universe, with the exception of black holes, which operate under a different set of physical rules. Neutron stars are the compressed, leftover cores of dead, massive stars. They are formed from stars that were large enough to end their lives in a supernova explosion, which then left behind this extremely dense central core. This core can contain up to 3 times the entire mass of our sun, all crushed into a sphere that is only 12 to 30 kilometers across. The material that makes up a neutron star is called neutron degenerate matter. It is a substance composed almost entirely of neutrons, packed together with no empty space. It is so densely packed that a single matchbox full of this material would weigh 3 billion tons if it were sitting on the surface of the Earth. This fact, however, leads to an interesting and important point about how we measure weight. The way we weigh something on Earth is by using a scale which measures an object pressing down. That downward force is a direct result of the strength of Earth's gravity pulling on the object. Yet, the measurement we often use to describe this, for instance, a person saying, "I weigh 70 kilograms," is actually a measure of mass, not true weight. Mass is the amount of stuff or substance in an object. Weight, by contrast, is the force that gravity exerts on that mass. A person's mass of 70 kilograms remains the same whether they are on Earth or on Mars. Their weight, however, would be much lighter on Mars, because the force of gravity is significantly weaker there. On a neutron star, all of that incredible mass being squeezed into the tightest of spaces means that the force of gravity on its surface is almost incomprehensibly strong. It is roughly 2 times 10 to the 11th, or 200 billion times stronger than the gravity we experience on Earth. It is difficult to put this number into perspective, but consider this. If a person were to fall from a height of just 1 meter above the surface of a neutron star, they would accelerate so rapidly that they would hit that surface at a speed of 1,500 kilometers per second. The gravity is so powerful, so extreme, that it bends space-time around it significantly. Light itself can be forced to go into orbit around the star. This means that at certain points, it is theoretically possible to see the entire neutron star at the same time as light from the back of the star is bent around toward the front. So, while this remains far outside the realms of any physical possibility, if a person were able to stand on the surface of a neutron star, their mass would be unchanged, but their weight would be 200 billion times greater than it is on Earth. It is difficult to imagine the sheer amount of force that body would be exerting on the floor of the neutron star. Not that the star would care in the slightest, given that it is already so densely packed. Of course, this scenario is purely a thought experiment. A fragile human body would not truly stand or weigh anything in that environment. The reality is that the body would be instantly flattened against the star's surface, crushed down to an atomic scale. The gravitational forces are so extreme that they would overcome the fundamental forces that hold atoms together, likely compressing the body's matter into neutron degenerate material itself. This same incredibly powerful gravitational field also has another effect. It pulls the star into the most perfect sphere in the universe. Any mountains or surface imperfections, even on a tiny scale, would be instantly pulled down by the immense gravity, making the entire object likely completely and unimaginably smooth. While neutron stars are a study of extreme gravity, other mysteries in our galaxy involve extreme energy. Approximately 800 light-years away from us, there appears to be an unseen antimatter factory. It is an object that is constantly churning out high-energy particles, specifically positrons. These are tiny particles of antimatter, the antimatter counterpart to our electrons, and they are streaming through the cosmos in all directions, with many colliding with our own planet. For most of human history, we were completely unaware that this strange source existed. The majority of the positrons that bombarded our world went entirely undetected. Instead, They were harmlessly absorbed as they interacted with our planet's upper atmosphere. We were shielded from them and blind to their presence. It was not until we developed the technology to send detectors beyond the bounds of our planet that we finally began to notice them. In the year 2011, NASA's Alpha Magnetic Spectrometer, a state-of-the-art and highly advanced particle detector, was switched on. It sits high aboard the International Space Station, orbiting far above the protective blanket of the atmosphere. Its primary mission was to catalog the various particles that make up cosmic rays, and as expected, it found positrons. The simple presence of these subatomic particles was not a surprise. We know of several natural processes that can create them, but the numbers were wrong. The sheer volume of positrons being detected by the spectrometer was far higher than anyone had anticipated. The usual known sources, such as natural radioactive decay or the byproducts of standard cosmic rays, could not offer a sufficient explanation for this surplus. There was simply too much antimatter arriving. This raised a critical new question. Where were all of these extra positrons coming from? It is only recently that scientists have been able to trace the likely culprit of this cosmic antimatter shower. The primary clue, it turns out, points back to a different high-energy discovery, one that was made decades earlier. This clue was a strange, diffuse, gamma-ray haze, given the name Geminga, which was first identified back in the 1970s. Up in our night sky, nestled within the boundaries of the Gemini constellation in the northern celestial hemisphere, there was something peculiar going on. In 1972, NASA's Small Astronomy Satellite 2, or SAS-2, identified an unknown and powerful source of gamma radiation. But with the technology that was available at that time, the best the satellite could do was trace its origin to a very wide, general region of our Milky Way. The radiation's ultimate source remained hidden among the countless stars for decades. Despite its mysterious nature, it had to be called something. In 1976, the Italian physicist Giovanni Bignami, who would eventually dedicate much of his career to studying this object, coined the name Geminga. The name itself is a clever play on words. First, it is a combination of Gemini, the constellation where it is located, and Gamma, for the type of radiation it emits. But it is also a pun in Bignami's native Milan dialect. The phrase Geminga translates to "it's not there," a perfectly fitting name for a powerful source of gamma rays that no one could actually find. For years, the mystery remained unsolved. Bignami and his team did not have their first big break until 1983. It was then that they finally managed to identify a weak X-ray signal originating from that same region using the Einstein X-ray satellite. This was a significant step forward. Although its precise position remained unknown, this X-ray data allowed them to narrow down their search area considerably. They were getting closer to uncovering Geminga's hiding place. But this discovery still did not answer the most important question. What is it? Astronomers could still only offer vague guesses about the true nature of the source. The next major leap forward did not happen until 1991. In that year, two separate missions had a lucky break. Operating independently, both identified radiation coming from Geminga, and crucially, what they found were not constant, steady signals. They discovered pulses. The first of these discoveries was made with a German-built X-ray telescope known as ROSAT, which is short for Roentgen satellite, named after the German word for X-rays. ROSAT was the first instrument to identify distinct, rhythmic pulses in the X-ray signal coming from Geminga. Very soon after this discovery, the same pulses were also confirmed in the gamma wavelengths. This confirmation came from the Energetic Gamma Ray Experiment Telescope, or EGRET, which was an instrument aboard NASA's Compton Gamma Ray Observatory satellite. These were complementary observations of the highest importance. They not only demonstrated that the X-rays and the gamma rays were both coming from the exact same object, but for the first time, they revealed what Jaminga was. The combined data showed an object flashing with a precise period of 0.237 seconds. It was spinning around on its axis a little more than 4 Hertz, or 4 times every second. This behavior was unmistakable. Jaminga behaved like a pulsar. A pulsar, as we know, is a type of rapidly spinning neutron star. It emits focused beams of radiation from its magnetic poles, which sweep across space like a cosmic lighthouse. From our distant vantage point across the galaxy, most pulsars appear to flash in radio waves. Their speeds can vary dramatically, flashing anywhere from a few times a minute to as fast as 700 times per second. At this point, in the early 1990s, gamma-ray pulsars were known to be incredibly rare. Before the ROSAT and EGRET observations, only 2 other high-energy gamma-ray pulsars had ever been identified, the famous Crab and Vela pulsars. But Jaminga was different. It did not fit the established mold. The Crab and Vela pulsars were different in a couple of key ways. First, in addition to their gamma rays, both of those pulsars also produced powerful and easily detectable radio waves. They were therefore clearly visible using radio telescopes on the ground. If Jaminga was indeed a pulsar, it was the first discovery of one that was apparently radio silent. It was only emitting enough radiation to be seen in the high-energy gamma and X-ray wavelengths, while remaining invisible to radio dishes. And second, the Crab and Vela pulsars are both surrounded by their respective vast nebulas. These are the visible, expanding remnants from the supernova explosions that created them. But Jaminga's nebula was conspicuous by its complete absence. This only raised new, more difficult questions. Why is Jaminga, this powerful source of gamma rays, so good at hiding from our radio telescopes? Where is its supernova remnant, its nebula? Or could it be a different type of object altogether? Well, the answer to that first question, why it seems so good at hiding from our radio telescopes, is complex, and it is in part because we hadn't been listening properly. This failure was not just due to the limitations of the technology available at the time, though that was a factor. It was also due to our scientific assumptions, our understanding of what the radio emissions from such stellar remnants were supposed to look like. The first pulsars we had found, like the one in the Crab Nebula, were extremely bright in radio waves. They created a pattern in our minds, a set of expectations for what a pulsar should be. Jaminga simply did not fit this pattern. You see, we now understand that radio pulsars, as a category, can emit energy across an incredibly wide range of frequencies, a vast bandwidth. This can stretch from as low as 17 megahertz, which is at the very low end of the radio dial, up to above 87 gigahertz, which is an extremely high frequency. This range covers around half of the entire radio spectrum. However, not all of these frequencies travel equally well through the vast, intervening space between the pulsar and us. We have known since the 1970s that radio pulsars are often intrinsically brightest at the low end of this range, somewhere between 100 and 200 megahertz. Intrinsically brightest means that if you were floating in space right next to the pulsar, that is where it would seem to shine the most. This fact would seem to make them easy to find. We should just listen at those frequencies. But the journey for that light is not simple. The universe is not truly empty. As those low-frequency signals make their way across the galaxy, they are progressively dampened and scattered. There are several things that get in the way. First is the interstellar medium. This is the thin, diffuse veil of gas and dust that fills the space between the stars. For a low-frequency radio wave, this medium acts like a thick fog for a car's headlights. It does not block the light completely, but it scatters it, making the source appear much fainter and more spread out. Second, the entire sky has a background temperature. It is not perfectly black and silent. There is a faint, constant radio hiss coming from all directions. A signal that is already very weak can easily be lost in this background noise, much like trying to hear a whisper in a crowded room. Finally, a third problem is our own planet's atmosphere. A specific layer high up, called the ionosphere, is notorious for reflecting or distorting low-frequency radio waves coming from space. It is like trying to see a clear image of a pebble at the bottom of a pond through all the ripples on the surface. When you combine these three effects, the interstellar fog, the background noise, and our own planet's atmospheric interference, it means that the very frequencies where the pulsar is naturally brightest, that 100 to 200 megahertz range, are ironically the most difficult to observe clearly from Earth. The signal that finally reaches our telescopes is extraordinarily weak, a mere ghost of its original strength. Because those low-frequency radio signals are so incredibly weak and difficult to untangle from the noise, most radio telescopes and astronomical surveys simply hadn't been looking for them. It was seen as an inefficient way to search for new objects. Instead, the common strategy was to confine the search to higher, cleaner frequencies. Astronomers chose a sweet spot in the spectrum, typically in a window between 430 and 1,600 megahertz. In this range, the interstellar fog is much thinner, and our atmosphere is more transparent. It was a logical and efficient strategy. They were looking for the pulsars that shined brightly in this clean window, and they found many. The assumption was, if a pulsar is out there, we will probably see it here. This strategy would have been perfectly fine if Jaminga had behaved as expected for one of its kind, but it did not. It was a pulsar that was only shining in that foggy, low-frequency window and was completely dark in the clean window everyone was watching. Since it did not fit the mold, it took until 1997 for scientists to finally realize what was happening. In that year, 3 independent observations, all originating from the Pushchino Radio Astronomy Observatory, were able to identify extremely weak pulses from Jaminga's location. They succeeded where others had failed because they were using a highly sensitive transit antenna, a specialized tool specifically designed to listen in that foggy low-frequency range. It was the right tool for the job, and the faint radio pulses they found came in at around 100 megahertz. This discovery was the key. It finally explained why all the previous radio searches for Jaminga had come up silent. It turns out Jaminga wasn't truly hiding. It had been sending us signals all along. We just weren't listening correctly. In that same year, a separate team led by the late astronomer Janus Gill theorized that there might be another reason Jaminga had appeared to be radio silent. This theory suggested the problem wasn't just the journey through space, but the pulsar itself. Their model showed that the pulsar's own magnetosphere, the intense, powerful bubble of magnetic energy surrounding the star, might be acting as a kind of internal filter. This magnetic field could be absorbing, or refracting or bending the radio waves that would normally be emitted at high frequencies, like 1,600 megahertz. This process would effectively choke off the signal, leaving the pulsar quiet in the very bands most telescopes used. But the model predicted this filter might be leaky, allowing a small amount of energy to escape, but only at the very low frequencies, around 100 megahertz. This theory was a perfect match for the observations from Pushchino. Confirming Geminga was a pulsar, and specifically a gamma-ray pulsar, was a very big deal. It was not just any pulsar. It was a completely new kind of pulsar. Most pulsars are like lighthouses that shine brightly in radio waves, but have a very dim, high-energy gamma-ray light. Geminga does the exact opposite. An astonishing 99% of its total energy output is not in radio waves, but in the gamma-ray range, the most energetic form of light. This makes it one of the single brightest and most powerful gamma-ray sources in our entire galaxy. We now understand that this object, this powerhouse of high-energy radiation, is all that is left after a star several times more massive than our Sun exploded in a supernova about 350,000 years ago. But its relative radio silence and its apparent lack of a nebula, that expanding cloud of debris from the explosion, were not the only unusual things about this pulsar. When Italian astrophysicists, including Giovanni Bignami, the man who gave Geminga its name, compared a series of observations taken over many years, they found something else. They used data from the European Southern Observatory's 3.6-meter telescope and its New Technology telescope, and compared those with observations from the Canada, France, Hawaii telescope. By comparing these images taken years apart, like a spot the difference game, they found that Geminga was moving. Not only was it moving, it was traveling at an unusually high speed across our line of sight, at a rate of around 0.2 arcseconds per year. As a reminder, an arcsecond is a very, very small unit of angular measurement. It is used in astronomy when we need far more precise measurements than a simple degree would allow. To understand the scale, you can think of the entire sky as a circle. That circle is divided into 360 degrees. If you stand outside and look from one point on the horizon, all the way across the sky to the opposite horizon, you are looking across 180 degrees. From the horizon straight up to the zenith, the point directly above your head is 90 degrees. There is a simple way to approximate this. If you hold out your arm at full length and raise your little finger, the tip of your finger covers about 1 degree of the sky. The next time you are outside on a clear night, you can try this and see if your little finger can cover the full moon. It should, very easily. The moon, which can look so large, actually takes up only about half of a degree in the night sky. That half a degree measurement is also known as about 31 arc minutes. This is where the units get smaller. Within each single degree, there are 60 equal parts, each called an arc minute. And within each one of those arc minutes, there are 60 even smaller parts, and these are called arc seconds. These arc seconds are a common unit used in astronomy to talk about the movement of objects across the sky from our perspective on Earth. So, when we say Geminga is traveling 0.2 arcseconds across our sky each year, it may not sound like a lot, but this speed must be put in context. A typical distant star in our galaxy only appears to move a few thousandths of an arcsecond per year. Geminga is moving hundreds of times faster than the average background of stars. Even though it is 800 light years away from us, this pulsar will travel a distance of 30 arc minutes, which is the equivalent to the entire apparent diameter of the full moon across our sky in just over 10,000 years. In other words, this stellar corpse is racing through the galaxy. This angular motion translates to a physical speed of nearly 210 kilometers per second. It is on a journey, heading towards the border between the constellations Gemini and Lynx. And at its current rate of motion, Jaminga will remain within the official boundaries of Gemini for another 500,000 years. But after that, it may just need a new name. However, the story of this mysterious pulsar gets stranger still. It turns out that its vast speed, the same incredible velocity that is carrying it on its journey across the constellation Gemini, is directly responsible for producing another feature, one that scientists were just about to discover. As this tiny, dense stellar corpse hurtles through space, it is not traveling cleanly. It leaves behind two ghostly tails. These are not tails made of gas or dust, like the ones we see trailing a comet. These tails are invisible to our eyes. They are made of pure, high-energy X-rays, and they are enormous, streaking a staggering 3 trillion kilometers across the sky. As I discussed earlier, despite the fact that this fast-moving pulsar is nearly radio silent, it is anything but quiet in the higher energy parts of the spectrum. Its brightest, most powerful voice is in gamma rays, but it also shines brightly in X-rays. To see this X-ray universe, we cannot use telescopes on the ground. Our planet's atmosphere, which protects us, completely absorbs this type of light. Therefore, we must go to space to observe it. In 1999, the European Space Agency, or ESA, launched a powerful new observatory to do just that. It was called the X-ray Multi-Mirror Mission, a satellite more commonly known as XMM Newton. This was a highly advanced and sensitive telescope designed with a special set of nested, cylindrical mirrors that could gently guide and focus incoming X-rays. Its mission was to peer deeper into this high-energy universe than ever before. XMM Newton began its work, and 4 years later, in 2003, a team led by astronomer Patricia Caraveo pointed this powerful instrument at Jaminga to get the best look yet. What they uncovered were these comet-like X-ray trails. They were faint, but they were unmistakably real, trailing behind the pulsar. The unique shape of these trails and their specific brightness could be partly explained by a concept known as a shock wave. This is a phenomenon similar in principle to the sonic boom a supersonic jet creates when it breaks the sound barrier in our atmosphere. But in this case, it is a bow shock in space. It is a wave created by Jaminga's extreme motion through the thin, almost non-existent material of space. This forward motion, combined with the pulsar's own rapid rotation, was the engine shaping this X-ray light. But these tales were more than just a curiosity. They were revealing of another fundamental attribute of Jaminga, its colossal mass. The object itself, the pulsar, is physically tiny. As we have established, a neutron star is the compressed core of a giant star that has died. Jaminga measures only about 20 to 30 kilometers across, about the same size as a large city. Yet, into this tiny volume, it contains about as much mass as 1.5 of our suns. The resulting density is difficult to comprehend. To put that in perspective, if you could somehow use a teaspoon to scoop up a tiny amount of this neutron star material, that single teaspoon of stuff would weigh about 4 billion tons on Earth. This is as much weight as 10,000 Empire State Buildings. This is the key to understanding the tales. We must look at how all these properties, the incredible speed, The immense mass, the tiny size, and the rapid spin all work together. This is where the physics combines to create the feature. First, we have this incredibly dense, high-mass object. It is racing forward. It is important to remember that it is not moving through a perfect, empty vacuum. It is traveling through what we call the interstellar medium. This is the extremely low-density material, mostly hydrogen gas, that fills the vast spaces between stars. In this particular region of the galaxy, that medium is incredibly thin, with only about 0.06 to 0.15 atoms per cubic centimeter. As Jaminga plows through this medium, its immense gravity and powerful motion act like a snowplow. It compresses this thin medium in front of it, and this medium has its own, very weak, magnetic field embedded within it. Jaminga's motion compresses both the medium and that magnetic field, making the field in its immediate vicinity much stronger than the surrounding space, by about a factor of 4. So, we have a fast-moving object that is creating a localized, enhanced magnetic field around itself. That is the first ingredient. The second ingredient is the pulsar's spin, the incessant, rapid spinning of the neutron star, 4 times every second, creates an environment of extreme and violent energy, especially around its magnetic poles. This environment is so powerful that it actually creates matter. It generates pairs of particles, specifically electrons, and their antimatter counterparts, called positrons. This pulsar wind of newly created particles is then accelerated to extreme energies, pushing them to speeds very close to the speed of light. These are the very particles that are powerful enough to emit the high-energy gamma rays that Jaminga is so famous for. Now, we can connect these two parts. Most of these high-energy electrons and positrons escape the pulsar entirely. They fly off into space in a beam, and this is the gamma radiation we detect, the voice of the pulsar. But some of these particles do not escape. They get caught. They are trapped by that enhanced magnetic field, the one Jaminga created by compressing the interstellar medium as it moves. Once these high-energy electrons are trapped, they can no longer fly in a straight line. The magnetic field lines force them to spiral, to corkscrew, around and around. And a fundamental law of physics says that when a high-energy charged particle, like an electron, is forced to bend its path and spiral in a magnetic field, it must shed energy. It releases this energy in the form of light. In this case, the particles are so energetic and the field is so strong that the light it sheds is in the X-ray spectrum. This is the source of the tails. They are the glowing paths of trapped particles spiraling in the magnetic wake of the pulsar. In images created from computer models that try to replicate this complex process, the tails can be seen clearly. They appear to streak along the edges of Jaminga's 3-dimensional shockwave. The analogy provided by the scientists is that it is like the V-shaped wake created by a boat moving through water. But in this cosmic example, the boat is an object more massive than our sun. It is moving at hundreds of kilometers per second, and the wake it leaves behind is not made of disturbed water, but of extremely high-energy X-rays. But even with the discovery of these X-ray tails, the final piece of the Jaminga puzzle was not discovered until 2005. It was its nebula. For decades, one of the main arguments against Jaminga being a pulsar was the fact that it seemed to lack a supernova remnant, that visible, expanding cloud of debris from the explosion that created it. But what we eventually found was a different, much more subtle kind of nebula. It takes the form of a faint, vast shell of neutral hydrogen gas. it is very large, with a radius of 0.4 parsecs wide. A parsec is a unit of distance used in astronomy, equal to about 3.26 light years. So this shell is very large indeed. This was finally identified as what we call a pulsar wind nebula. So, what is a pulsar wind nebula? And how is it different from a supernova remnant? A supernova remnant is the explosion itself. It is the material from the original star's outer layers thrown outwards into space. A pulsar wind nebula, or PWN, is something created after the explosion by the pulsar that was left behind. This type of nebula is created from the wind that emanates from the pulsar's magnetic poles. This wind, as we just discussed, is not like a breeze on Earth. It is a powerful plasma, a stream of superheated charged particles, those same electrons and positrons. These particles are accelerated to near light speed. This wind flows outwards at incredible speed, surrounding the pulsar, and it eventually calls with the slower moving interstellar medium, or perhaps with the inside edge of the old, faded supernova remnant. This collision creates a shock, and this bubble of high-energy particles begins to glow, giving off strong emissions, particularly X-rays. With the confirmation that Geminga did have a nebula, this pulsar wind nebula, its identity as a pulsar could finally be and truly confirmed. The case was closed, but this only led to the next, deeper mystery. Another powerful X-ray observatory, NASA's Chandra X-ray Observatory, was brought in to look at the puzzle. In addition to imaging Geminga, scientists used Chandra to look at a second pulsar, an object known as B0355+54. For simplicity, we will just call this one Pulsar B. By comparing these two objects side by side, astronomers uncovered another possible explanation for the central mystery of Geminga: its baffling, decades-long absence of bright radio pulses. This is a powerful scientific technique, finding two objects that are very similar and then focusing on the one major way they are different. On the surface, these two pulsars seem quite similar. They are both estimated to be about the same age, roughly 500,000 years old. They also spin at a similar rate, about 4 to 5 times per second. For many purposes, they could be considered cosmic twins. However, as we know, their behavior, their light, is completely different. Geminga is seen primarily in gamma-ray pulses. It is one of the brightest gamma-ray sources in the sky, but it has no bright radio emissions. By contrast, the other pulsar, Pulsar B, is the exact opposite. It is not seen in gamma rays at all. It is gamma ray silent. Instead, it is one of the brightest known radio pulsars in the entire sky. How could these two pulsars, which are so similar in their fundamental properties, be so vastly different in how we see them? We have two objects of roughly the same age, about 500,000 years old, and spinning at a similar rate, around 4 to 5 times per second. Yet, one, Geminga, is a blazing gamma-ray source but is radio silent. The other, Pulsar B, is a brilliant radio source but is gamma-ray silent. The answer, astronomers believe, may be as simple and as elegant as geometry. It is not about what these pulsars are, but about how each of these objects is oriented relative to our observation point here on Earth. Astronomers believe that these images from the Chandra X-ray Observatory, when combined with our models, have finally revealed the orientation of their spin axis. This, in turn, has uncovered a clear reason for why radio pulses and gamma ray pulses may be present or absent on different pulsars. Let's break down the model. Like our own planet Earth, which has a geographic North Pole and a separate magnetic North Pole, both of these pulsars have magnetic poles that are close to, but not perfectly aligned with, their spin poles. From our previous discussions, we know that these magnetic poles are the source of the powerful, focused beams of pulsing radio emissions. We can try to model this with a simple analogy. Imagine you have a small foam ball. This ball represents the pulsar, the neutron star itself. Now, take a long, thin wooden skewer and push it straight through the ball from one side to the other. This skewer represents the pulsar's magnetic axis. The two sharp ends of the skewer sticking out of either end of the ball represent the two narrow beams of radio emissions. Now, if you spin the ball around an imaginary line, its spin axis, those skewer ends, will sweep around the sky, just like the beam of a lighthouse. This creates the pulsing radio signal. Now, we need to add the gamma rays to our model. The gamma rays are not thought to come from the poles. Instead, they are believed to be generated in a wide, flat sheet, or a torus, that beams out from the pulsar's spin equator. This is the middle of the spinning ball. To illustrate this, you could cut a hole in the center of a paper plate and squeeze that plate over the foam ball so the plate sticks out horizontally while the ball spins. Now you have a complete model. A spinning ball with two radio beams, the shooting from the poles, and a flat disk of gamma rays, the paper plate shooting out in all directions from the equator. With this model, the difference between Jaminga and Pulsar B becomes obvious. It is all about the viewing angle. In the case of Jaminga, we on Earth are positioned so that we are looking at this model edge on. The edge of the paper plate is pointing directly towards us. This means we are flying right through that flat sheet of gamma rays. So we detect a powerful, pulsing gamma ray signal. But where are the radio beams? Because we are looking at the system from the side, the skewer is oriented horizontally. As the pulsar spins, those radio beams are sweeping up and down or side to side, but they are pointing far away from us. They are completely missing Earth. Now, let's consider Pulsar B. Its relative position to us is at a completely different angle. It is as if we have floated above the model and are now looking down at the flat surface of the paper plate. From this angle, the gamma rays, which are only shooting out from the edge of the plate, are all moving perpendicular to our line of sight. They are completely missing Earth. But what are we seeing? We are looking almost straight down the spin axis, which means we are looking right into the path of the radio beam, the end of the skewer as it sweeps around. Let's look again at the two Chandra images to see the evidence for this model. We have Jaminga on the left and Pulsar B on the right, along with artist illustrations of what astronomers believe the pulsar wind nebulas look like for each. In the image of Pulsar B, the long, trailing blue tails are interpreted as the radio jets emanating from its poles, the ends of our skewer. They are not straight, like our wooden skewer. This is because Pulsar B is moving so fast through space that these jets are being bent backwards, trailing behind the pulsar as it moves, much like the wake of a boat. The key is that these jets are oriented in a way that suggests one is pointing generally toward us and the other generally away from us. Now, look at the image of Jaminga. We also see tails, but the orientation is completely different. The long twin tails, which are also the radio jets, are seen trailing off to either side of the image. This is the visual evidence that matches our model. This is the skewer seen from the side. The jets are pointing sideways relative to us. They are not aimed at Earth. So, as Jaminga rushes through space, its radio jets are bent back, but they remain pointed off to the side, and our radio telescopes detect nothing. So, when astronomers look at Jaminga, they see powerful gamma-ray emissions from the spin equator, the edge of the paper plate. But the radio jets, the skewer, point off to the sides and remain unseen by us. And when they look at pulsar B, the opposite happens. The radio jets are pointed almost straight toward our planet, while the gamma-ray source at the equator is angled in a way that it is completely missing Earth. The two pulsars are not fundamentally different. We are simply seeing them from two different perspectives. Sometimes the most simple explanation is the correct one. And that finally brings us back to the decades-long mystery of an unusual abundance of antimatter bombarding our planet. For more than a decade, a highly sophisticated particle detector has been attached to the outside of the International Space Station. This instrument is called the Alpha Magnetic Spectrometer, or AMS-2. Its purpose is to orbit high above the Earth, acting like a giant, sensitive net, catching and identifying the various energetic particles that travel through space. These particles are known collectively as cosmic rays. Cosmic rays are not a form of light. They are physical bits of matter. They are fragments of atoms, protons, electrons, and heavier nuclei that have been accelerated to tremendous speeds, traveling at nearly the speed of light. These particles are created by different processes in the universe. Some are fired off by our own sun, while others are blasted out by cataclysmic events like supernova explosions, the death of a massive star. In 2013, the first major results from the AMS-2 experiment were announced, and they were significant. The detector had, in a short time, recorded more than 400,000 positrons. A positron is the antimatter counterpart to an electron. This single data release represented the largest sample of cosmic ray positron data ever collected, increasing the world's total data on this specific particle by 100-fold. But the most important finding was not just the number, but the ratio. There were far more of these positrons than our existing theories could explain. For years, this excess antimatter was one of the most exciting mysteries in physics. Many astronomers and physicists hoped that this signal might be the long-sought-after byproduct of dark matter. This was a very compelling idea. After all, we believe dark matter makes up around 27% of the entire cosmos, yet we still have no idea what it actually is. Like the regular matter that makes up our bodies and our planet, dark matter clearly has mass. We can see its gravitational pull holding galaxies together, and it takes up space. But it does not seem to absorb, reflect, or interact with light in any way we can detect, making it completely invisible. Some theories proposed that dark matter might be made of yet unidentified particles. A very popular theory suggested that if two of these hypothetical dark matter particles were to collide, they would annihilate or destroy each other. And in that flash of destruction, they would create a shower of normal, detectable particles, including, perhaps, the very positrons that AMS-2 was counting. Scientists had high hopes that this overabundance of antimatter being detected from the space station might finally hold the clues to dark matter's true nature. Unfortunately, as more data has been collected, they have been left disappointed. The more scientists dig into the precise details of the data, the clearer the picture becomes. The most likely source of these extra positrons may not be exotic and new at all. They may be coming from pulsars. Astrophysicists had long suspected this. We know that pulsars naturally surround themselves with a haze of both electrons and their positron counterparts. This is a direct result of the star's intense, rapidly spinning magnetic field. This field is so powerful that it literally rips particles from the pulsar's surface and accelerates them to near the speed of light. These accelerated particles then collide with low-energy starlight that is passing by, boosting that light to much higher energies, which we then observe as a gamma-ray halo. This was a good theory, but until 2017, there simply was not enough proof. The High-Altitude Water Cherenkov Gamma-Ray Observatory, or HAWC, finally provided the first piece of hard evidence. The HAWC Observatory detected a small halo of extremely high-energy gamma radiation surrounding Geminga. This light had trillions of times more energy than what our eyes can see, specifically in the range of 5 to 40 trillion electron volts. This is exactly the sort of radiation that is expected to be produced by high-energy positrons. This was the first real observational evidence pointing to a pulsar as the source. However, there was a problem. Based on the size of the halo that the HAWC team saw, the positrons seemed to be contained in a relatively small bubble around Geminga. If they were trapped that close to the pulsar, they would rarely have the energy or ability to escape and travel all the way to our planet to be detected. And so, many believed the excess positrons must still have a more exotic source, perhaps dark matter after all. That was the situation until stunning new information was uncovered just a few years later. This new discovery was thanks to a team led by astrophysicist Mattia Di Mauro, who used a different instrument. Instead of HAWC, they used a decade's worth of gamma-ray data from Fermi's Large Area Telescope. The crucial difference is that the Fermi telescope is able to observe lower energy gamma-ray light than the HAWC observatory. Using this decade of data, Di Mauro's team was able to carefully subtract out all the other known gamma-ray sources in that patch of sky to see what, if anything, was left behind. What they revealed was a spectacular glow coming from Geminga, but it was much, much bigger than what scientists had ever seen before. This vast, oblong halo of glowing gamma rays, seen at an energy of 10 billion electron volts, a lower energy than HAWC was looking at, spanned 20 degrees of the sky. For perspective, this is a similar area to the one the Big Dipper constellation occupies, and that is not all. The glow of gamma radiation is even bigger at lower energies. If our eyes were sensitive to this light, Geminga's gamma-ray glow would dominate our sky, covering an area 40 times bigger than the full moon. With this new information, the puzzle was solved. Astrophysicists found that the enormous size of this lower energy halo meant that the positrons were not trapped. They were, in fact, leaking out and traveling vast distances, far enough to easily reach Earth. The calculations showed that this one pulsar, Geminga alone, could be responsible for as much as 20% of the total excess positrons detected near Earth. From there, it is no stretch at all to imagine that the thousands of other pulsars in our galaxy are the most likely culprit for the remaining antimatter abundance we have found. This explanation may not have solved the deep mystery of dark matter, but it is, in itself, a magnificent revelation about the power and influence of these tiny, dead stars. It was Jocelyn Bell who discovered the first pulsar back in 1967. At the time, the signal was so strange, so perfectly regular in its repeating pulses, that it was unlike anything astronomers had ever seen. This regularity was so precise, so seemingly artificial, that it was briefly, and half-jokingly, considered that it might be a signal from an extraterrestrial intelligence. In the nearly 60 years that have passed since that first detection, we have of course, identified the true source. These are not alien beacons, but the natural lighthouse-like beams from rapidly spinning neutron stars. We have now found thousands of them, and our understanding of these dense, exotic objects has grown with every new one we catalog. When Geminga was finally confirmed as a pulsar in 1991, it was only the third such object known to emit most of its powerful energy in the form of gamma rays. It was part of a very exclusive and mysterious club. Today, thanks to advanced orbital missions, particularly NASA's Fermi Gamma Ray Space Telescope, we have spotted over 300 of these gamma ray pulsars. But given Geminga's specific and unusual track record of defying our expectations, of being radio silent for so long, of possessing those strange X-ray tails, and of being a source of antimatter, it is likely that this particular pulsar still has more secrets to reveal. If one were to tune into the universe with the right kind of equipment, it becomes clear that the cosmos is humming. This is not a sound in the way we normally think of it. Of course, the vacuum of space does not permit sound waves to travel. Instead, we are talking about a different, more fundamental kind of vibration. This is the persistent background hum of gravitational waves. We are already familiar with a similar kind of background signal, one that was discovered decades ago. This is called the cosmic microwave background, or the CMB. The CMB is a faint, persistent glow of microwave light. It is not coming from any single star or galaxy, but is coming from everywhere in the sky, in all directions. This glow is the afterglow of the Big Bang itself. The discovery of this leftover heat from creation was a groundbreaking moment in science. It was the smoking gun, the undeniable evidence that solidified the Big Bang's place as the leading theory of our universe's beginning. Yet, this light signal, as important as it is, has a glaring weakness. It is the earliest light of our universe, but it was only emitted almost 400,000 years after the Big Bang. It cannot show us what happened before that moment. In those first 400,000 years, the universe was so hot and so dense that it was completely opaque. It was a fog of plasma, and light could not travel freely through it. This means the cosmic microwave background cannot, by its very nature, tell us anything about what happened within those first crucial moments. If we want to go back earlier, to probe the conditions of the Big Bang itself, we will need a different kind of background signal. We need one that is not made of light, but of the ripples in the fabric of space-time. Gravitational waves are not blocked by hot plasma. They travel unimpeded from their source. In 2023, astronomers at the Nanograv collaboration announced that by using a clever trick, they may have detected just that. By using exotic stars as a galactic-sized gravitational wave detector, they measured the faint hum of space-time itself. This hum of gravitational waves might just be the reverberations of the very creation of our universe. This new discovery opens an entirely different window than the one used by ground-based detectors like LIGO. The LIGO detector operates by using lasers. It shoots these lasers down very long, perpendicular tunnels to precisely measure the minuscule changes in the length of those tunnels. These changes are caused by gravitational waves passing through the Earth. As a wave passes, it stretches space-time in one direction and simultaneously squishes it in the other. This causes a tiny, temporary change in the time it takes for the laser light to travel from one end of the tunnel to the other and back again. But detectors like LIGO, which are only a few kilometers long, are only sensitive to a specific kind of gravitational wave. Like light waves and sound waves, gravitational waves can come in many different frequencies. This is the gravitational wave spectrum. LIGO is only able to listen in to one part of this spectrum, the very high frequencies. These high-frequency waves are generated by objects that are spiraling in on each other very rapidly. This is the violent end stage of a merger, where two black holes, or two neutron stars, are completing hundreds of rotations every second, just moments before they collide, in a great, energetic bang. But that is also precisely why LIGO cannot listen in on the much earlier stages of these binaries. It cannot hear the processes that take place when the objects are still orbiting each other at a much greater distance. Because these orbits are much slower, perhaps taking years or even decades to complete one lap, the gravitational waves they produce are of a much, much lower frequency and a much lower energy. So, rather than a great bang, these slow, massive orbits give off a faint hum, and because there are thousands, perhaps millions, of these massive binaries all orbiting slowly throughout the universe, their individual faint hums combine. They all overlap, merging into one persistent, collective signal. This is the background. In this cosmic chorus, the bigger black holes give greater contributions to the signal. The loudest individual contributors would consist of pairs of supermassive black holes. These are not the small, stellar mass black holes that LIGO detects. These are the truly massive kind, the ones you would find at the very center of large galaxies. We are talking about binaries, which consist of two black holes that are billions of times the mass of our Sun. These pairs are expected to be rare, because they only form when something truly spectacular and violent happens. This process is the merger of two galaxies. When these massive structures collide, it is not a violent crash in the way we might imagine. Galaxies are overwhelmingly composed of vast amounts of empty interstellar space. Because of this, when they merge, their stars and planets mostly phase through each other. They pass by one another like two intermingling clouds of mist. Very few, if any, actual collisions of stars or planets happen. But the gravity from all these billions of stars interacts on a massive scale. The stars are gravitationally attracted to one another. Their orbits are scrambled and pulled, and over millions of years, they merge into one larger, collective galaxy. But what happens to the dense centers of these galaxies? The nuclei, which are the supermassive black holes at their hearts, are the heaviest objects in the system. They are pulled by gravity and sink toward the new center of this merged galaxy. They form a binary system, a pair of supermassive black holes, and they continue orbiting one another long after the visible stars of the galaxy merger appear to be complete. It is these leftover remnants, these massive pairs of orbiting giants, that we would hear most strongly in the ultra-low frequency range of gravitational waves. Specifically, this is the nanohertz range, meaning the waves have extraordinarily long wavelengths. This corresponds to the black holes themselves having very slow orbits, perhaps taking years to complete one circle. Just as the human ear cannot hear sounds with ultra-low frequencies, our current ground-based detectors, like LIGO, are deaf to this cosmic cacophony. LIGO is built like a very sensitive microphone to hear the high-pitched chirp of small black holes colliding very quickly, hundreds of times per second. It simply cannot hear the deep, slow, persistent hum of these giant binaries. If we could listen in to this low-frequency hum, we would gain completely new insight into how galaxies merge and how these supermassive black holes grow over cosmic time. But that is not the only reason this is so exciting. One of the most profound things about this low-frequency gravitational wave background is that it is a window to the very first moments of our universe's existence. Let's quickly recap what we know about the other background signal, the cosmic microwave background, or CMB. This microwave light is the afterglow of the Big Bang. It is the earliest light that we can detect. We can see this light because it was emitted almost 400,000 years after the Big Bang, but this also means we cannot see any light from before that time. It creates a wall for our telescopes. What does it mean for the universe to be opaque for those first 400,000 years? In its initial state, the universe was far too hot and dense for neutral matter to exist. The building blocks of atoms, electrons, and protons were unable to bind together. They simply had too much energy and were moving too fast. This state of matter, this hot, charged soup of free-flying electrons and protons, is called a plasma. It is the same stuff that our sun and all other stars are made of. And in the beginning, the entire universe was filled with it. Light finds it almost impossible to travel through plasma. A particle of light, a photon, would get trapped. It would be emitted, but it would immediately bump into a free-floating, charged electron, which would absorb it. That electron would then re-emit the photon in a completely random new direction, where it would immediately bump into another electron. It was like a person trying to walk through an impossibly dense, chaotic crowd. They are constantly being bumped, absorbed, and scattered, unable to make any progress in a straight line. But the universe was expanding, and as it expanded, it cooled down. Once the universe cooled enough, at that 400,000-year mark, the protons and electrons could finally slow down enough to coalesce. They bound together, forming neutral hydrogen and helium atoms. In that instant, the universe suddenly became transparent. The crowd of chaotic electrons had suddenly paired up with protons, and the photons were finally freed. The light was now able to travel in long, straight, uninterrupted lines. This light, which was freed when the universe was 400,000 years old, has been traveling ever since. As it traveled through the expanding universe, the fabric of space itself was stretching underneath it. This stretching pulled on the light waves, lengthening their wavelength and redshifting them from a hot, bright glow into the cool, faint microwave light that we detect today. This is why the cosmic microwave background is the earliest light of the universe. But gravitational waves are not made of light. They are not particles traveling through space. They are made of space-time itself. They are ripples in the very fabric of reality. That plasma soup was no obstacle to them. To gravitational waves, the universe has been transparent from almost the very instant of the Big Bang. They are not a particle in the fog. They are a vibration of the fog itself. They can penetrate past this plasma barrier, this 400,000-year wall, and offer us a glimpse of the very first moments of the universe's creation. Because these primordial gravitational waves, the ones from the very beginning, have also been traveling for so long, they too were stretched by the expansion of space-time. Just like the CMB light, their frequencies were lowered. They were redshifted into ultra-low frequency gravitational waves. This is the crucial connection. They were stretched into the same kind of low-frequency band that would come from the supermassive black hole binaries. Together, these multiple sources, the distant chorus of merging black holes, and the ancient echo of the universe's creation, will give us a so-called stochastic gravitational wave background. This is not one clean signal, but a combined, overlapping hum existing over a range of low frequencies. So, How can astronomers actually retrieve this treasure trove of information? We know this low-frequency hum, this background of gravitational waves, is almost certainly out there. It is carrying secrets about the merger of supermassive black holes and, perhaps, the echo of the Big Bang itself. How do we listen to it? A natural first thought is to ask, can we simply build a better LIGO? Can we design a new instrument, perhaps in space, to detect how the Earth, or the detector itself, is bobbing up and down, being gently stretched and squished by these gargantuan, universe-spanning waves? The short answer is no. This approach will not work, and the reason comes down to a fundamental and non-negotiable mismatch of scale. To understand why, we must first look at how LIGO works. LIGO, as we have discussed, is a ground-based detector. It operates by sending two powerful beams of laser light down two very long, perfectly straight tunnel arms. These arms are placed perpendicular to each other, forming a giant L shape. At the far ends of each of those tunnels, which are 4 kilometers long, there are incredibly precise, almost perfect mirrors. These mirrors reflect the laser beams, sending them straight back to their starting point. At that starting point, the two returning beams of light are combined. They are overlapped and compared with each other. In a perfectly still and quiet universe, the light waves from both arms would return at the exact same time. They would interfere in a very specific, predictable way, effectively canceling each other out. The whole point of this setup is to detect tiny, tiny distortions in space-time. When a high-frequency gravitational wave from a distant collision passes through, it will, for a tiny fraction of a second, stretch one arm of the detector and simultaneously squish the other. This means the laser in the stretched arm has to travel a slightly longer distance, while the laser in the squished arm travels a slightly shorter one. They arrive back at the starting point just slightly out of sync. This tiny, tiny difference, this mismatch in their arrival time, is the signal. This is how LIGO hears a black hole collision. But this brilliant design has a critical limitation. It only works if the arms of the detector are roughly the same size as, or at least a significant fraction of, the wavelength of the wave it is trying to detect. If we wanted to design a new LIGO to detect these ultra-low frequency gravitational waves, we would need to build tunnel arms that are much, much larger than anything we could ever build on Earth. This is because of a fundamental property of all waves. The frequency of a wave is inversely proportional to its wavelength. This is a simple but crucial concept. A high-frequency wave, like the chirp LIGO hears, means the wave crests are very close together. It has a short wavelength. An ultra-low frequency wave, like the hum we are searching for, means the wave crests are incredibly, unimaginably far apart. It has an ultra-long wavelength. To notice the effect of a wave that is so stretched out, you must measure the change over a much, much greater distance. Trying to measure a wave that is tens of light years long using a detector that is only 4 kilometers long is like trying to measure the tide of the entire ocean using a teacup. The instrument is simply too small to register the change. Let's look at the specific scale we are dealing with. We are searching for waves in the nanohertz range. A hertz means 1 cycle per second. A nanohertz means 1 cycle per billion seconds. This is a single, full fluctuation, one wave crest, passing by over a span of about 30 years. We can do a quick calculation. The wavelength of any wave is equal to the speed of the wave divided by its frequency. The speed of a gravitational wave is the speed of light. The frequency is 1 per billion seconds. This calculation tells us that the wavelength would be around 10 to the power of 17 meters. This number is so large it is almost meaningless by itself. We need a sense of scale. The distance from the Earth to the Sun, which we call 1 astronomical unit, is about 10 to the power of 11 meters. A single light year, the distance light travels in an entire year, is around 10 to the power of 16 meters. The wavelengths we are discussing are 10 to the power of 17 meters. This means a single wave is tens of light years long. Clearly, we cannot build a detector suitable for this task. It is not possible on Earth. It is not even possible within our solar system. The entire solar system is just a tiny fraction of one of these wavelengths. We would need a detector that spans a significant portion of our stellar neighborhood. But rather than wait for humanity to somehow ascend beyond the confines of our solar system and become an advanced, spacefaring civilization capable of building such structures, astronomers at Nanograv have used a clever trick. They realized they did not need to build a detector. The detector already exists, scattered across our galaxy. As we have discussed, there is a special class of object in our galaxy known as a pulsar. These are ultra-dense neutron stars, the collapsed cores of dead giant stars. They are remarkable because they spin with the most unwavering stability. As they spin, they emit powerful beams of light radio waves along their magnetic poles. These beams sweep around the cosmos like a lighthouse. From our perspective on Earth, we see a pulse of radio light every time that beam sweeps past us. These pulses come with such precise certainty, such a reliable rhythm, that they are used as the clocks of the cosmos. They are the most stable timekeepers we know of, able to keep time with incredible accuracy across vast distances of thousands of light years. Therefore, astronomers realized they could use these already identified pulsars to supply them with reliable signals. These signals travel from thousands of light years away, passing through the very space-time that we want to measure. In this new galactic-sized detector, the pulsars act like the mirrors at the end of the LIGO arms. But there is one key difference. In LIGO, we send a laser to the mirror and wait for it to come back. Here, we cannot do that. Instead, the pulsars are generating their own perfect, clock-like signal and sending it to us. The scientists at Nanograv have, in effect, cleverly concocted a natural interferometer. It is a detector that does not use just 2 arms, but uses dozens of arms at once. 1 arm for every pulsar they monitor. This detector stretches for thousands of light years, across a huge swath of our galaxy. And the best part is how we use it. We do not need new, futuristic technology. All we need to read the signals from this giant detector are the good, old-fashioned radio telescopes that we have already been using for decades. But our calculations will only be as good as our observations. The entire premise of this galactic scale detector rests on the quality of our data. When choosing the pulsars to observe, we need to be absolutely certain that they are suitable for this incredibly delicate task. This is not a job for just any pulsar. The best candidates are hand-picked, meticulously studied, and then added to a group that astronomers call a pulsar timing array. For the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, they have made use of 68 pulsars. These were not chosen at random. They were chosen because they possess a specific set of special properties that make them ideal for this experiment. First, These 68 pulsars had to be spread all across the sky. This is a critical requirement. If all our clocks were clustered in one small patch of the sky, we could only measure the effect of a gravitational wave in that one tiny direction. We would have no context. To truly understand the wave, we need to see how it is affecting space-time in all directions simultaneously. We need to be able to compare a pulsar in the northern sky with one in the southern sky. This allows us to build a three-dimensional map of the wave as it passes through our section of the galaxy. Second, and most importantly, they had to be millisecond pulsars. A typical pulsar, like the one in the Crab Nebula, might spin once every few seconds. A millisecond pulsar is a different class of object entirely. They spin hundreds of times every single second. This incredible speed makes them the most stable and dependable clocks in the known universe. Their stability comes from a simple principle of physics: gyroscopic inertia. A spinning top that is moving very, very fast is incredibly resistant to being knocked over. A millisecond pulsar, with all the mass of a sun packed into the size of a city and spinning at nearly the speed of light, is the ultimate gyroscope. This extreme stability is what makes the regularity of their pulses so precise. In fact, their stability, the reliability of their tick, rivals that of some of the atomic clocks we have built here on Earth, which are our most advanced timekeeping devices. We simply could not ask for better, more reliable timekeepers to be dotted across the vastness of space and time. This profound regularity is what makes the whole experiment possible. It means that we can take precise measurements of the time that their pulses arrive at Earth. We can then continue taking these measurements over multiple years, building up a long, detailed record. With this record, we can then look for any tiny changes, any deviations from the perfect clock-like signal we expect. Of course, the arrival times can vary due to all sorts of factors. There are predictable delays, first and foremost. The most obvious one is the motion of the Earth and the pulsar. As the Earth moves in its orbit around the Sun, it sometimes moves slightly closer to a pulsar and sometimes slightly farther away. This changes the travel time of the pulse. But because we know the Earth's orbit with extreme precision, we can take this into account quite easily. We can calculate this predictable orbital delay and subtract it from our data. However, there are also less predictable factors. The biggest challenge is noise. The signal from a pulsar, which is just a beam of radio waves, has to travel for thousands of light years to reach us. The space it travels through is not a perfect vacuum. It is filled with random, wispy clouds of interstellar gas. As the light travels through this thin, intervening fog, it can be subtly delayed. These delays are random, and they are not caused by the stretching of space-time. This is the noise. How do we get rid of this random noise in our data? We are looking for a signal, the gravitational wave that is billions of times fainter than this noise. How can we possibly isolate one from the other? The answer is with statistics. We can isolate the gravitational wave background from the random noise by considering correlations between pairs of pulsars in our array. This is where the true genius of the pulsar timing array becomes clear. As the source text mentioned with LIGO, one tunnel is not sufficient. You need two perpendicular arms to measure the difference between the stretching in one direction and the squishing in the other. The same principle applies here, but on a galactic scale. We need to compare pairs of our pulsars. Imagine you are monitoring your 68 pulsars. If the signal from one pulsar suddenly arrives a few nanoseconds late, you would probably ignore it. You would assume it was just a random delay caused by that interstellar fog on that one specific path. But what if you saw a pattern? What if you saw that a pulsar in one part of the sky was arriving late, and at the exact same time, a different pulsar in a different part of the sky was arriving early? If similar fluctuations show up across 2 or 10 or all 68 pulsars at the same time, it becomes highly unlikely that this is random. It is almost impossible that the random noise for each pulsar just happened to align in such a perfect way, by pure chance, to make them all appear to act in unison. It is far more likely that there is a common cause underlying all of those fluctuations. That common cause would be a single, massive gravitational wave, so large that it is washing over all of them at once. As the wave passes, it might be stretching the space-time that the photons from one pulsar are traveling through, while simultaneously squishing the space-time for photons coming from another pulsar. We can then take these correlations and relate them to the angular distance between the pulsars, how far apart they appear in the sky. If there is no gravitational wave background, we would expect there to be no correlation. The timing of one pulsar would have nothing to do with the timing of any other. The graph of their relationship would just be a straight, flat line at zero. However, if the data shows a very special, specific curve, a shape known as the Hellings and Downs curve, that would be the smoking gun. It would be the undeniable signature indicating that a gravitational wave background is responsible for the variances. This specific curve, predicted by physicists decades ago, is the unique mathematical fingerprint of gravitational waves, and only gravitational waves. That is precisely what the Nanograv collaboration has succeeded in doing. On the 28th of June, 2023, they announced their results. Based on over 15 years of continuous, patient observations of their 68 pulsars, they announced strong evidence for the existence of this gravitational wave background. The graph they published is the graph we have been waiting for. It plots the correlation strength on one axis and the angular separation on the other. And the data points, collected over 15 years, trace the exact shape of the Hellings and Downs curve. This is the hallmark of gravitational waves, which, as we know, stretch space-time along one direction and squish it in the perpendicular direction. This is exactly what the graph is showing. For example, when pulsars are separated at right angles in the sky, 90 degrees, their photons are experiencing an opposing effect as they travel to Earth. The error bars in the data, which represent the uncertainty, appear quite large, but the researchers have calculated that the data shows the existence of this curve is statistically significant at the 3 sigma level. What this means is that there is only a 1 in 1,000 chance that this is a false alarm. It is the chance that all that random noise over 15 years just happened to mimic this exact perfect curve by mere chance. In physics, the 5 sigma level is considered the gold standard for an official discovery, but 3 sigma is still very, very strong evidence. It is the point where scientists are confident they are seeing a real, physical effect. As they continue to collect and analyze more data, the error bars will shrink, and they will likely, finally, be able to announce an official discovery. So, what secrets does this new gravitational wave background reveal? While we cannot pick apart the individual sources of this collective noise just yet, the future is bright. We hope that these techniques will eventually allow us to listen in to specific, individual supermassive black hole binaries, and perhaps even hear the signal from the creation of the universe itself. Until then, astronomers will continue to use their new galaxy-sized detector to calculate how we are all, right now, bobbing up and down in the turbulent sea of space-time. Every year, since 2018, astronomers have spotted a mysterious, brilliant blue flash somewhere in the night sky. When we say bright, it is hard to overstate the scale. This is one of the brightest phenomena in the entire universe. It is an explosion so luminous that it makes an average supernova, the violent death of an entire star, look like a faintly lit candle in the far distance. Some of these events have been spotted relatively close to us, in our own galactic neighborhood. Others have been seen billions of light years away, near the edge of the observable universe. They all look similar enough to one another to suggest they are the same class of object, but no one knows what they are or what causes them. Through rigorous observation and painstaking analysis of the few events we have seen, astronomers began to decode a pattern. They started formulating a tentative but plausible theory for what these flashes could be. And then, in 2023, they saw something new, something that did not fit the pattern at all, and it left them completely baffled. These explosions are officially called luminous fast blue optical transients. Because that name is so long, astronomers simply refer to them as LFBOTs, or LF-bots, and there is simply nothing else like them out there. Being such a recently discovered event, the data we have on LF-bots is minimal. This is a brand new field of study. The very first LF-bot ever detected and confirmed was identified just 6 years ago, in 2018, and in the time since, we have only managed to witness a handful of them. Because so little is known about them, and our sample size is so small, it makes agreeing on a universal definition for them a little tricky. Scientists are still figuring out what the rules are for this category. For now, what they do all agree on are some common characteristics that these LF-bots seem to share. So far, they all display a predominantly blue emission. This tells us that the event is incredibly, extraordinarily hot. They also have a very high optical luminosity, which is the scientific way of saying they are stunningly bright to our eyes, or at least to optical telescopes. They are also bright in other invisible parts of the spectrum, like X-rays, ultraviolet light, and radio waves. They are also very fast, as their name indicates. An LFBOT goes off like a cosmic camera flash. They reach their peak brightness, their maximum intensity, and then they dim very, very rapidly. This entire process usually takes place in the space of just hours or days. As you might know, a supernova follows the same general pattern. It brightens, reaches a peak, and then dims. But for a typical supernova, this dimming process is slow and gradual. It takes weeks, or sometimes even months, for the light to fade away. This short-lived, transient nature of LFBOTs is precisely what makes them so difficult to spot and even harder to study. You have to be looking at the exact right place at the exact right time, or you will miss the entire event. So, how did we manage to capture such an elusive event in the first place? The discovery was, in large part, an accident. It was made by NASA's Atlas telescope in Hawaii. Atlas is not one single telescope, but a system of them. Its primary job is to act as an early asteroid impact warning system. To do this, It scans the entire sky over and over, several times every single night, looking for small moving objects, asteroids that might pose a threat to Earth. On the 16th of June, 2018, Atlas was performing this routine scan. It was just another night taking pictures of the sky, comparing them to pictures from a few hours earlier. But its automated systems flagged something very unusual. It was not a moving dot. It was a stationary flash, a new point of light that had not been there before. This flash was 100 times brighter than a regular supernova. And then, within just a few days, it was gone. The scramble was on. As soon as the alert went out, scientists around the world immediately started analyzing the data to understand what they had just seen. They pinpointed the explosion as coming from the Hercules constellation at a distance of about 180 million light years away. The event was given an official automatic designation at 2018 Cow. Because of the last 3 letters in its name, the event was affectionately nicknamed the Cow. Once located, the first step was to try and classify it. The object was quickly, and perhaps a bit too hastily, classified as a Type 1b supernova. This is a known kind of explosion. It is also known as a core collapse explosion, which is formed when a truly massive star, one that has lost its outer layers of hydrogen, finally runs out of fuel and collapses under its own immense gravity. But something about this particular explosion did not quite fit. When astronomers took a closer look at the Cow's emission spectrum, the fingerprint of the light, which tells us what elements it is made of, it did not look like a typical Type 1b supernova. It had unusually broad emission lines and, crucially, very weak helium lines. Scientists thought it appeared more reminiscent of a different, rarer category, a Type 1c supernova, and so it was quickly reclassified. However, the more that scientists pored over the data from all the different telescopes that had turned to look at it, the more surprised they were by what they found. Whatever this explosion was, it started to look less and less like any kind of supernova. At least, not the kind of supernova we thought we understood. For starters, it appeared out of nowhere. This blast went from being completely inactive to reaching its peak luminosity in just a few days. As we mentioned, supernovae usually take months to reach their brightest point and then dim again at a similarly slow pace. This was far too fast. Not only that, but it was registered to be 10 to 100 times brighter than an ordinary supernova. This was an incredible amount of energy being released in a very short amount of time. Also, everything about the way it exploded was wrong. When supernovae explode, they tend to release their energy in a roughly spherical shape. The blast wave expands outwards in all directions, like an inflating balloon. We do know now that the shock waves sent out after a supernova can be aspherical or lopsided. This is often due to the presence of strong magnetic fields, which can channel the energy and distort the shape of the initial blast. However, upon closer inspection, this mystery explosion did not just explode aspherically, it was extremely aspherical. The researchers themselves called it the most aspherical explosion ever seen. It seemed to be a flat, disc-like explosion, not a ball-like one. Soon enough, the supernova theories were being abandoned and new, more exotic theories were being put forward. Some astronomers thought the Cow could be a monster black hole that was shredding a passing star apart an event known as a tidal disruption. Others suggested that it was a supernova, but a very special kind, one that, in its final collapse, gave birth to a brand new, rapidly spinning black hole or neutron star, and this central engine was powering the strange light. But let's step back for a moment. It is incredibly difficult and scientifically risky to draw any firm conclusions when you only have one of something. In science, a single data point, like the cow, is an anomaly. It is a curiosity, not a rule. As the saying goes, once is an anomaly, twice is a coincidence, but 3 times, that is the beginning of a pattern. What researchers truly needed was a bigger sample size. They needed more instances of this kind of explosion so they could compare the observations. They had to look for common threads, for shared characteristics, and deduce any patterns that might arise from the data. Luckily, it did not take long for scientists, who were now actively searching for these signals, to get their eyes on a second, similar explosion. A few months later, in September of 2018, the cosmic camera flashed again, and then it flashed a third time in 2020. Keeping with the informal tradition of pulling animal nicknames from the last 3 letters of their official designation, the cow was joined by the koala and the camel. And just like that, what was once a single, baffling event was now a class of objects. Astronomers had data on 3 separate LFBOT events. The hunt for patterns could finally begin in earnest. When analyzing the data from the cow, the koala, and the camel, one of the first things that stood out to researchers was their location. Even though they all happened in completely different parts of the universe, each blast was registered as coming from the same type of neighborhood. They were all found deep inside the spiral arms of their host galaxies. At first, this information seemed to embolden the initial theory that LFBOTs were just a very strange, very bright type of core collapse supernova. Let me explain why this location was such a strong piece of evidence. The kind of star that is massive enough to cause a core collapse supernova is one of the biggest, hottest types of stars you can get. And as we know, the bigger and more massive a star is, the shorter its lifespan. They burn through their nuclear fuel at an incredible rate. This means that these massive stars do not get the chance to travel very far before they die. A star's life is a race between its lifespan and its orbital motion around the galaxy. A small star like our sun will live for billions of years, orbiting the galaxy many times. A massive star lives for only a few million years, which is not enough time to drift away from its birthplace. It would make perfect sense then that their supernova explosions occur very close to the star cluster where they were born. And what part of the galaxy is known for having these rich clusters and stellar nurseries? The spiral arms. This is where the dense gas and dust are, which is the raw material for star factories. The fact that we saw all 3 LFBOTs in these exact active regions made the supernova theory look very promising. But just as researchers seemed to be making progress, something happened that caught them completely off guard all over again. Like the Atlas system in Hawaii, the Zwicky Transient Facility, or ZTF, is another very wide-angle, ground-based camera. It is designed to scan the whole northern sky every 2 days, specifically looking for transients, things that flash, change, or move. In 2022, it detected another, similar blue explosion. But after the initial, blinding flash, this optical transient started behaving rather strangely. Instead of exploding once and fading away in a few days, like the other LFBOTs before it, this new event which was nicknamed the Tasmanian Devil, continued to produce more flashes. It kept bursting. It produced short duration, powerful bursts, far longer than anyone expected. What's more, each of these subsequent bursts seemed to be just as bright as the original main explosion. This was very strange indeed. The Tasmanian Devil emitted more energy than hundreds of billions of stars like our sun combined, and it did it over and over. Researchers were deeply puzzled yet again. It was unlike anything they had ever seen before in astronomy. This was not just a technical error. It was not a case of miscalibrated equipment or a simple mathematical mistake. The history of science is full of such moments, but this was not one of them. The data was corroborated. 14 other telescopes around the world were alerted, and they turned to look. They confirmed that the Tasmanian Devil did, in fact, pulsate a minimum of 14 times. The total number was likely much higher. Equally surprising, these mega powerful pulses were separated by only minutes. It looked to scientists like a star that was trying to die, exploding, and then somehow being revived and exploding again and again. If that is what it was, this strange phenomenon could provide brand new insight into the very last moments of a star's life. In short, even though the multiple bursts of light from the Tasmanian Devil were completely unexpected, there was still reason to suspect these explosions could have been a very strange, complex type of supernova. None of the observations directly violated the core collapse supernova theory. It was just a much more complicated version of it. But what came next did. On April 10th, 2023, astronomers picked up yet another big blue explosion. It had all the same characteristics: the blue color, the incredible brightness, the fast fade. It was clearly one of their LF-bot zodiac relatives, except this one was not even close to where it was supposed to be. Unlike all the other LF-bots before it, this new event, the Finch, was not in the spiral arm of a distant galaxy. It was not in a galaxy at all. It was found 3 billion light years away from us and 15,000 light years from the closest visible galaxy. It stood solitary in the deep darkness of intergalactic space. It was in the middle of nowhere, exploding in the vast, empty gulf between two galaxies. This was a huge blow to the leading theory. If these explosions really were the result of massive stars' core collapsing, there is no known way it could be happening out there. Massive stars are not born in the empty void between galaxies. The star factories simply do not exist there. So, it was back to the drawing board for researchers. They came up with 2 new theories to explain what could have caused the Finch to explode where it did. The first suggests that the Finch could be the result of a star being torn apart by an intermediate mass black hole, or IMBH. This is a middleweight black hole, one that has 100 to 10,000 times more mass than our sun. We have confirmed that small, stellar black holes exist, and we have confirmed that supermassive black holes exist. But this middle child remains purely theoretical. Their existence has never been proven. However, if they exist, could they be responsible? Astronomers have shown in simulations that a star could be captured in orbit around an IMBH. With each orbit, the star gets shredded, losing more and more of its mass to the black hole's gravity. Finally, the remaining stellar matter would be torn apart completely and flung back out into space at speeds as high as 10% the speed of light. This violent, tidal disruption would be consistent with the speed and brightness observed in LF bots. This theory could also explain the location. One of the most likely places researchers would expect to find IMBHs is in the center of globular star clusters. These are ancient, dense balls of stars that orbit in a galaxy's outer halo. A galaxy's halo is a vast, spherical region that extends far beyond the main visible disk. It is possible that the Finch was not in empty space at all, but was inside a very faint, distant, globular cluster, part of a galaxy's halo that we simply cannot see from 3 billion light years away. The second theory researchers put forward suggested that the Finch was the result of 2 neutron stars moving towards each other in increasingly tight spirals until they collided. This kind of event is called a kilonova, and it is known to be one of the biggest stellar blasts in the universe. A kilonova would be powerful enough, and it involves objects, neutron stars, that are old enough to have been kicked out of their home galaxy and drifted into intergalactic space. But this theory has its own data problems. One telltale sign of a kilonova is the presence of gravitational waves, a chirp signal caused by the rapid spiraling. As bad luck would have it, our chirp detector, the Laser Interferometer Gravitational Wave Observatory, or LIGO, was down for maintenance at the time the Finch occurred. We have no data on this. We also know that no gamma ray burst was detected, which is something you might expect to see with a kilonova. But this explosion happened 3 billion light years away. That is really far, perhaps too far for whatever gamma ray data there might have been to be detected. All in all, none of this data can conclusively confirm or reject the neutron star theory. It is frustrating to witness such a rare, new, and powerful phenomenon and not have the data to understand its cause. Scientists are already planning to use the powerful optics of the James Webb Space Telescope to carry out a search for any faint globular clusters in the same location as the Finch. This would clarify if they are on the right path with the intermediate mass black hole theory. In the meantime, other researchers are focused on broadening the sample size. The more LF bots we can detect, the more we will learn. The half dozen we have seen so far have taught us some things, but mostly they have raised more questions. The only way we are going to get a larger sample is to keep sweeping the sky with wide-field surveys. Scientists' hopes are pinned on the Vera C. Rubin Observatory, currently under construction in Chile. It is expected to be operational by 2025 and will scan the entire southern sky every few nights. It will find more LF bots, and that is when the real learning will begin.